Today we're going to solve trigonometric equations. So these are any equations that have one of the 6 functions in the equation. So we're going to do, well, a variety of different problems, but 2 main types here. Notice the first example versus the second. Here we want to find all possible solutions, and of course that means there's going to be an infinite number of solutions. In the second example, we're going to restrict our solutions to only those in the interval 0 to 2 pi. So we are going to handle these types of problems differently, and that's why I separated them. Some of these will be a little more challenging because notice like H and I in the first problem, E, F in the second problem, they have a change in the period, so that affects how we get our solutions. And we'll talk about those when we get to them. So really no new results to learn in this section. It's just learning how to do the problems. So that's why I just have a bunch of examples here. And I'm just going to write them down on a different piece of paper. So the first example, let's call it example 1, part A. This would be, would consider this a pretty basic, straightforward problem. Whenever you're solving these, you always want to isolate the trig expression first, see which number, what the output needs to be, I should say. And then you can figure out what x would have to be to give you that output. So when we do this, we say, okay, well, sine is negative in quadrants 3 and 4. Reference angle would be pi over 3 in this case, because the sine of pi over 3 is the square root of 3 over 2. So you pick the values in quadrant 3 and 4 that would give you negative square root of 3 over 2. So we say, okay, well, from here we can conclude, or it follows, that x would have to be 4 pi over 3. That would be the quadrant 3 solution. Or x would be 5 pi over 3. That's the quadrant 4 solution. But then we want all solutions, so then we will add the period to that, or subtract the period. And so the k here stands for any integer. All right, and z stands for the integers. So positive and negative whole numbers, in other words, and 0. Zoom out a little, you can't even see that. Oh, that's not going to let me do that. Try this. Oh. I'll have to move the paper over. Okay, so this z that I'm using, these are the integers. So k can be 0, which means you have 4 pi over 3. K could be 1, then you have 2 pi. 2, you're adding 4 pi. 3, you're adding 6 pi. And then it can also be negative, and that's when you're actually subtracting. So, take it times negative 1, then you're subtracting 2 pi. Negative 2, you're subtracting 4 pi, and so on. So use k or use n. I can't remember what WebAssign uses. They probably use n. It doesn't really matter which one you use. So you need to do that also with the solution in the fourth quadrant. So this would be all possible solutions then. Whoops. Circle both of those. Right? So 4 pi over 3 and any number that if we say angle, any angle that is coterminal to it, and 5 pi over 3 and all coterminal angles as well. However, keep in mind that these, we can consider these to be real numbers as well, right? These are lengths. And we don't want to use degrees in these solutions. If you use degrees, I'm going to take off a lot of points. You should be using real numbers here. So answer using real numbers on all of these. Never want to see you using degrees. Okay, so let's go on to the next one. Again, this one is pretty straightforward because the tangent is already isolated. I don't know why I wrote square root of x. That should be square root of 3. There. So we know we want where the tangent is equal to the square root of 3. That means the reference angle is again pi over 3 like in part A. But this is a positive square root of 3. Tangent is positive in quadrants 1 and 3. So again, with the pi over 3, but in quadrant 1, pi over 3. Whoops. Sorry. It's early. I'm not awake yet. X equals pi over 3 there. Or x equals in quadrant 3, again, 4 pi over 3. So with tangent, remember the period is pi. So you can write these separately if you want. Whoops. Just like we did before, add 2 pi k. K again is an integer. And that would be fine. But notice with tangent, because so say this is the unit circle here, x squared plus y squared equals 1. Pi over 3 is here, right? Pi over 3, and then this one is 4 pi over 3. These are pi units apart. Whoops. And of course, we know the period is pi. Since they're an equal distance apart, you could just write x is pi over 3 plus pi k. So I would accept both of these. This is okay, but this is actually more concise. And so I would say this is, I don't know, it's not necessarily better. I think, well, I guess I think it's better, but this is more concise. Helps if I know how to spell concise there. Right, so this would be how you would see it, like if you were looking at a textbook and look at the answers in the back of the book, it's going to look like this. But it's okay on the test if you do this. So notice when you add the pi to this, it gives you the 4 pi over 3, right? And then when you add another pi to that, you'll get the 7 pi over, wait, what did I say? Yeah, 7 pi over 3, which is what you would get for this one if you added the 2 pi. So this one hits all the answers, just, you know, written in a shorter way. That's why I say it's more concise, but this is okay. That only works for tangent because the period is shorter, right? Pi. This, the here, the sine and for cosine, and secant and cosecant, period is 2 pi. I said it only works for tangent, but it works for cotangent as well. Excuse me, for its reciprocal as well, because they both have a period of pi. All right, so let's go on to C. So we have 2 cosine x plus 1 equals 0. This one is a little bit harder because we have to isolate cosine of x first. So isolate cosine of x. Whoops, I started writing of x. Cosine of x, we'll just write it like that. So you would move the 1 over, subtract 1, and then divide both sides by 2. Cosine of x equals negative 1/2. So again, we have a reference angle of pi over 3. Apparently like that reference angle today. Right, cosine of pi over 3 is 1/2. But cosine is negative in quadrants 2 and 3. So this would imply cosine, excuse me, not cosine x. This is x now. We've solved for x. X is 2 pi over 3, that's quadrant 2, plus then add multiples of 2 pi, or x equals 4 pi over 3 in quadrant 3, and again, any multiple of 2 pi could be added or subtracted. So there's our solutions. Again, k is an integer. If you don't remember to do that in your work, that's okay. We'll assume k is always an integer in our work. Okay, so when you're doing this cosine, you know, remember that's a function, and we are then looking at this and saying, okay, what could I put in here? This is what can go in place of x to give me this result. Now we know about the inverse functions, and you might be wondering why we're not using those. Well, you can use the inverse function, but it gets real tricky with that, because the inverse function, if you write x equals cosine inverse of -1/2, that only represents this solution. So then you have to get fancy to write the answer for 4 pi over 3 in terms of cosine inverse. So it's just easier to just say, okay, which two solutions, there's going to be two that give me a negative, which ones are they, and then add the period to those. So we don't use cosine inverse unless we have to, and sometimes we have to, and that's when this number, the output, isn't for one of the special angles. But so far everything we've done, we know, we should have these values memorized from the unit circle. So we don't want to do this unless we have to. We'll get to one of those eventually. All right, let's do another problem. So D, we have cosecant squared x minus 4 equals 0. So cosecant squared x equals 4. And remember, this means cosecant squared x is cosecant x squared. So we can take the square root of both sides to get cosecant x, but when we do that, we have to use the square root property. So cosecant x can be positive 2 or negative 2, and this will be true. So there's actually, oops. So what's going to happen is we're going to have a solution in every quadrant if we take one trip around the unit circle, right? We got all the positive and the negative values. Now we could have, I did use this, took the square root of both sides here, but you could have also factored that. That's cosecant, oops, my parenthesis became my c, cosecant x plus 2 times cosecant x minus 2 equals 0. Set each factor to 0, and then you end up with these two equations as well. So both of those methods work fine. Turn this light off. I think it works better without the light. Okay, so of course cosecant x equals 2 would be the same as saying sine of x equals 1/2. So we have reference angles of pi over 6, cosecant and slash sine are positive in quadrants 1 and 2. So for this first equation, we get x is pi over 6. That's not a 6 at all. I'm seeing this 2 here. Pi over 6 plus pi k. And then in quadrant 2, we have 5 pi over 6 plus 2 pi k. Sorry. For the second equation, now cosecant is negative in quadrants 3 and 4, so we get x is 7 pi over 6 plus 2 pi k, and then x is 11 pi over 6 plus 2 pi k. All right, and the reason I keep skipping the pi k is because I'm thinking about like we can actually condense these if you think about it, because we're talking about reference angles of pi over 6. We'll notice that's exactly pi away from 7 pi over 6. So these two here could be combined as pi over 6 plus pi k, But you don't have to. If you don't notice that, that's okay. This would be perfectly fine. So you could do x is pi over 6 plus pi k to represent the pi over 6 and the 7 pi over 6 and 1. And then 5 pi over 6 and 11 pi over 6 will be pi units apart. And so you could also combine those two. So all of these 4 statements can be condensed into 2 actually. But it's fine if you answer with the 4 statements. All right, E. Now we have 6 cosine x plus 5 equals 0. So subtract 5 from both sides, of course, and then divide by 6. Cosine x is negative 5/6. So here's where things get a little trickier because negative 5/6 is not an output for one of our special numbers, special angles, inputs. So here we're going to have to use cosine inverse. So if you think about the unit circle, cosine is negative in quadrants 2 and 3. So when you use cosine inverse, that is representing the solution in quadrant 2. So in other words, cosine inverse of negative 5/6 is between, it's less than pi, bigger than pi over 2, right? Quadrant 2. So we get just, this notation just represents this one solution, and then you can add 2 pi k to get other solutions. So how are we going to get this solution? How are we going to represent that? Because this is not a nice number, right? This is going to be an irrational number. Well, what we can use are reference angles. So this here is cosine inverse of negative 5/6, but this angle here, again, I'm using the word angle, but it can also just, it can be this length. This would be pi minus that. So if I want, so let me just call it theta sub r, that's my reference angle. If I want to get the angle in quadrant 3, this angle here is going to be the same size as this. I want to put that in there, and so I'm going to take that and add it to pi. So the other solution would be pi plus our theta r, right, which is pi plus pi minus cosine inverse of negative 5/6. And, or pi plus pi is 2 pi minus cosine inverse of negative 5/6. Okay, so once you have, now, well, let me talk about this. So think about what this means. Remember, this here, or this angle, is, call it theta. Theta is cosine inverse of negative 5/6. So this is saying 2 pi, go all the way here, and then subtract that angle. See, you get back, if you subtract theta, which this is theta, you're back to where you want to be. So this number here, 2 pi minus cosine inverse of negative 5/6, is in the third quadrant. Okay, this is not easy to, this is not a natural thing to do. So you need to think about this for a while, make sure you understand how to do this. So this is in quadrant 3. You can certainly plug these into your calculators and verify that this one is bigger than pi over 2 but less than pi. This one is bigger than pi but less than 3 pi over 2. If you're not sure if you got the right answer, you can use your calculator to test it. But I don't want those approximate answers. These would be the exact answers. Okay, now we're not quite done here because we still need to add multiples of 2 pi k. So here are 2 solutions. I mean, it's more than 2 solutions, right? I mean, the two statements that represent all solutions. That's theta. That's definitely a harder problem. Whenever you don't have, whenever your output is not for one of the special angles or special numbers, things get a little harder. So we don't like to use those inverse notations unless we have to. That's why we avoid them for these problems. Because if we used it for here, we'd have to do this technique for those as well. It's easier just to come up with the other angles. All right, but let's go on to F. F is 3 sine x minus 10 equals 0. So if we add 10 and divide by 3, we get sine x is 10 thirds. So this is, at first seems like we're going to have to do the same thing we did in the last problem. But you have to be paying attention here. Notice that 10 thirds is bigger than 1. And sine of x is always between -1 and 1. So this one has no solution. Now if that were a 1/3, we would handle it the same way as that cosine problem, but because it's a 10 thirds and bigger than 1, no solution. So sine and cosine, remember those are always between -1 and 1. Tangent and cotangent have a range of all real numbers. So those, if this were a tangent or a cotangent, you can always solve that. Secant and cosecant are, those outputs need to be -infinity to 1 or 1 to infinity, right? So make sure your output here is actually in the range of your function. In other words, in the set of possible outputs, right? Okay, so let's move on to G. We have tangent squared x equals 1. All right, so again with the square, that means you have, when you take the square root of both sides, right, this is similar to D actually, we get tangent of x is plus or minus 1. So again, we'll have a solution in every single quadrant. So this, this is short, you don't have to write this in, but it's short for tangent x is -1 or tangent x is 1. So the first one, x would be, well, let's do the positive one first, right? We get pi over 4. And then also in quadrant 3, 5 pi over 4. But since those are pi of pi plus pi k. And then -1, we'd have 3 pi over 4. And then that's quadrant 2. In quadrant 4, we'd have 7 pi over 4. And so again, pi units apart plus pi k. So you can leave it like that. Or if you're paying attention, you notice that these are all pi over 2 apart. You can actually combine this. Whoops, this should still say pi over 4. But this one should say pi over 2. Like that. Okay, so that's an or. You don't have to do both. Because on the unit circle, right, you got pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. These are all pi over 2 units apart. Since they're equally spaced, you can write just one statement. That's all I'm saying there. But again, you don't have to do that. All right, now let's do H and I. These are a little harder because of the period change. Cosine of 3x equals square root of 2 over 2. So no, you can't divide the 3 out of there or anything like that. You have to work with this 3x. So if this number in here is pi over 4, or 7 pi over 4, right? Cosine of pi over 4 is square root of 2 over 2. Cosine of 7 pi over 4 is square root of 2 over 2. Cosine's positive in quadrants 1 and 4. So you need to figure out what value of x here would give us pi over 4. And the answer is pi over 12. 3 times pi over 12 is equal to pi over 4. So this 3 affects what these numbers will, you want these numbers in the cosine, but it affects what the x will be, I should say. So this is actually going to be the x, right? So then the output, you're actually taking cosine of pi over 4. Well, you don't have to really do what I did here and come up with it like this. What you can do is say, okay, well, I want this in here to be pi over 4. So I'm just going to say, okay, well, I need 3x to equal pi over 4. And then I also need to adjust for all of the other solutions. And the period of cosine is 2 pi. So if I add 2 pi k, that would give me another solution here every time, right? So then I can just divide everything by 3, both sides by 3. The original solution plus the period. And when I divide everything by 3, I get x equals, notice the pi over 4 divided by 3 is really pi over 4 times a third. And so I get that pi over 12 I was talking about. And my period changes. And of course, if we were just looking at y equals cosine of 3x, we would say, okay, period is 2 pi over b, 2 pi over 3, right? So this is one set of solutions, but we still have another set. And that is if 3x is the 7 pi over 4 that we talked about. And then add the period to that. So just divide all of this by 3. So x equals 7 pi over 4, I'll just write it times 1/3, plus 2 pi over 3k, or x is 7 pi over 12 plus 2 pi over 3k. Here's the rest of the solutions. So notice when you put the 7 pi over 12 in, the 3 goes into 12 4 times, and you get the 7 pi over 4, right? And then when you add this period, you're going to get other solutions. Notice pi over 12 plus 2 pi over 3. Usually got to be good with working with fractions here. We want a common denominator, which would be 12. So I'll take this times 4 over 4. 4 times 2 is 8. So we'll get 8 pi. 3 times 4 is 12. So now I've got 9 pi over 12, which actually simplifies because these are both divisible by 3. So divide both by 3, and I get 3 pi over 4. So that what this is saying is that this value of x, if I plug it into here, I'm going to get a solution. So note, now I just did this for one possible solution. There's many others, of course. Cosine of 3x would be, I'm checking this one, 3 times 3 over 4, which is cosine of 9 pi over 4. And 9 pi over 4 is in back to quadrant 1, right? Notice the pi over 4 was in quadrant 1. If you add 2 pi to that, you get the 9 pi over 4. And so this is square root of 2 over 2. So this method will get you all of the solutions. First, come up with your main solution, what the multiple angle would be, right? 3x is a triple angle, 3 times x. So I'm just using the generic multiple angle to stand for any scenario. What that would have to be, plus the original period, divide by that number, and you'll get everything adjusted like you need it so that you get all solutions. So you have to do it for all possible signs, right? These are both positive. This is all positive, but if this were a plus or minus, you'd have 4 statements. Okay, so we have another one in part I. I'll just flip the page over here. So in I, we have 2 sine of 1/2 t plus square root of 3 equals 0. So again, this is in the argument of the function. You can't do anything with that. But the stuff outside, you can subtract the square root of 3. And then divide both sides by 2. But your argument, that's inside the operation of the function. You can't take that out of there, so that stays in. So now we say, okay, well, for sine, I recognize negative square root of 3 over 2. The reference angle would be pi over 3, and sine is negative in quadrants 2 and 3. So we would need whatever this number is here, this 1/2 t, would have to be 2 pi over 3 in quadrant 2, and then again add multiples of 2 pi k to get coterminal answers, or looks like a plus sign. I want to make sure it looks like a t. 1/2 t is 4 pi over 3 in quadrant 3. Again, add multiples of 2 pi k. So now we're going to divide everything by half, which it's easier to think about as multiplying by 2. So multiply through both sides times 2. T equals 2 times 2 pi over 3 is 4 pi over 3 plus 4 pi k. Notice that's our period of the sine of 1/2 t. 2 pi over a half is 4 pi. Or, so do the same thing on the other solution, multiply everything by 2. T equals 8 pi over 3 plus 4 pi k. And that's it. Those are all of your solutions. So if you remember to add your period first before you solve for t, you get the correct adjustment of the period, and it makes it a lot easier to come up with the solutions. So notice if you go back and check 4 pi over 3, the 2 will go into 4 2 times, and you've got the 2 pi over 3. Sine of 2 pi over 3 is negative square root of 3 over 2. 2's cancel. Negative square root of 3 plus square root of 3 is 0. And you can, of course, check any answer. But there is an infinite number of solutions, of course. All right, well, so these are the ones. So with the all solutions, you should always have the period added to the function, right? When we do the next example, we're going to have to look at it a little bit differently because we don't want all solutions. We only want a certain number of the solutions. But this is a good place for a break, so I'm going to stop the video here, and we'll come back to those other problems.